What is interesting to see is that roughly today 80% of the design contains analog IPs, and there's many reasons for that, including the largest SoC today that are mainly digital. They contain a lot of IPs that are analog based, for example, to drive the touch screen, to drive the wireless access, and so on and so forth. So analog is pretty much everywhere. From a design size point of view, this analog only represents pretty much 20% of the size. But if you look at things from more a complexity point of view and risk point of view, it's pretty much 75% of the risk we could estimate. So this is a very critical aspect, and what is interesting to see is that there were no real changes in this flow in the past 10 years. And that's the reason why Mentor Graphics has decided to invest into this area, mainly in two domains, which are silicon-aware design solutions, and another domain which is time-to-silicon productivity tools and solutions. So to serve this market, we have introduced recently a tool called Pixis that will allow people to do two things and more, but more specifically, we have developed features in two areas. The first area is about concurrent engineering, and the second one is about automatic routing. I think everyone knows what is concurrent engineering. That's a technology that has been used and developed a lot into the PCB area. It allows several engineers to work on the same design at the same time. So we're introducing the same technology within the IC design domain, and this is going to be very useful for designers so that they can work at the same time on the same chip, but also very useful at the time of the physical verification of the chip. With the most advanced nodes, the physical verification of the analog IPs are getting quite complex and causes a lot of problems due to variability. And so here the idea is to allow you to link the physical verification with the design process so that you can, while you design, verify that what you're designing is going to be correct according to the design rules. And what we've done is that we've introduced a technology called Caliber Real Time, which allow you, as you design, to check what you're doing. And in the past, people could afford to design and then check. But today, with the amount of rules you have to check and the complexity of the designs, you need to enter into a loop when you do both at the same time. And this is exactly what this tool is doing. By adding a tool called Caliber NMDRC, which is a sign-off tool within the design flow, you are able to verify as you build. And this is very, very efficient type of methodology that will allow you to be very confident about the end result, and also will allow you to go through and prepare the sign-off process, because the tool you're using to do the verification is based on the same technology as the one you're going to use for sign-off. So this kind of technology, the link between Pixis and NMDRC through Caliber Real Time, is going to provide you value very immediately. The other type of technology we've been working on is in the domain of automation. We have introduced a tool that allows you to automatically route your analog IP, and this at the transition, at the cell, at the block, and even at the top level of the chip, which is quite unique on the market. For example, Marvell, we are in Israel, and Marvell is quite an important customer in this area. Marvell has been running some tests on a portion of an IP they had, an analog IP, and the work that they have been doing in almost a week with that IP, the routing work, they've been able to do it in a matter of a few minutes. And at the same time, they've been able to shrink the size of the layout by a third. Using this automated router. So we strongly feel that by continuing to introduce new features and new tools of that kind within our IC flow, we're able to change the way analog designers are working today, and we are able to provide them more automation that should bring better quality type of IP in a shorter amount of time. So more announcement will come in the coming months and years. Design closure is getting more and more difficult to achieve as we get to more advanced nodes, and this is due to different effects introduced by new processors as well as variability. So people are looking for more accurate extraction and simulation that will make them confident that they will be able to reach the yield that they are looking for without going through the cost of an expensive over-design. So the objective for them is, how can I get an accurate simulation of my system in the shortest amount of time? And today, mainly you have two solutions. One is to use the classical field solver kind of extraction tool that are very accurate, but have a lack in terms of performance and capacity. Or you can go to the long time known classical rule-based type of extraction tools that have the speed, but maybe have a problem of accuracy. And for that reason, Mentor have been working on new type of approaches and new type of algorithms, and we are introducing a tool called Calibre Exact 3D that is based on an algorithm called finite element method and boundary element method that will provide you the accuracy of the field solver and at the same time a very good speed and a very good accuracy. The other very good thing about this algorithm is that it is deterministic, which means that your results are going to be repeatable. Each time you simulate, you get the same results, which is going to make you more confident into the result of the simulation, and so you will not be pushed to over-design to compensate for this level of uncertainty. So that technology being part of the overall Calibre sign-off flow, and for example linked with Calibre LVS, will allow the designers to tackle in a very efficient way the most advanced nodes and reach to a result that will provide them maximize yields in a very, very quick way. Today we talk more and more about SoCs, but also about, for example, 3D ICs. And these systems have a lot of interfaces. We're talking about thousands of interfaces that would go outside of the package. And what we tend to realize is that managing this system that will include the chip itself, or the chips, because you may have several chips into one package, the package and the PCB in isolation is going to be a challenge. It's very difficult to get to an optimized solution if you separate the problem. So what we need now is to get a tool, a solution that will allow you to analyze into one environment all the problems that you will face at the chip level, at the package level, and at the PCB level. Being able to deal with things like the routing of the signals and everything related to the signal integrity and things like power. Because if you think about a system like this, you could imagine to have signals that will go out of a chip, that will go through some balls, and from the balls that will go down into an interposer, and then into the interposer some signals might go back into another chip, or will go down through another ball and then to the PCB. All that is quite complex to manage, and the problem is that it's not only going to be a question of how you're going to route all these signals through all these elements, but it's also about how the signal will be treated and how it will be affected by this routing, how the power will be affected as well. And the problem is that if you want to get to the optimized solution and to the solution that will be the most cost-effective as well as with the best performance, you need to take into consideration all these elements at the same time. So that's the reason why Mentor Graphics has been working on providing solutions that allow you to plan these things and bring into one environment all the knowledge of the people in charge of the IC, in charge of the package, in charge of the PCB, into one platform, to a kind of a BGA planner type of platform that will allow them to bring their knowledge, bring their constraints, and so that we can come up with the most optimized solution in terms of the time it takes to develop it, as well as in terms of cost. Both cost at the chip level, at the package level, as well as the PCB level.
Hi, my name is John Cooley. I run something called Deep Chip, which is a 20-year-old mailing list of chip designers. Started out in Boston about 20 years ago, and it was just a handful of Synopsys users using this tool called Design Compiler. And that was 20 years ago, and it's expanded into this huge discussion involving anything to do with IC design and EDA tools associated with that. So that could be discussions about Mentor, Cadence, Synopsys, Magma, Apache, Tanner, IC Manage, oh God, just the laundry list goes on. Eve, I'm trying to think of companies now. But it just goes and goes and goes. But what it is basically 30,000 chip designers discussing EDA tools and their bugs and their workarounds. And it's kind of a no bullshit forum. It's not marketing, it's real, what really works, what doesn't work. I wanted to talk to Israeli engineers, chip designers and specifically, about the importance of their personal reputation and having to get known outside of Israel. What I found is in Israel, everybody knows everybody. It's a small little community. Every designer knows everybody. All these little companies all talk to each other. Everybody knows everybody's secrets. But what's missing and what kind of doesn't help Israel is your outside reputation. You spend a lot of time networking with each other in Tel Aviv and Herzliya and all in the greater area. But you want to get yourself known outside of Israel, and that means going onto the web. What that doesn't mean is going onto Facebook and LinkedIn and Twitter. It means getting into the uncontrolled forums like what I run, Deep Chip, and talking about tool talk, really going to town on various tools and what you've specifically seen with them. If you're using, for example, let's say you're using scan tools. What do you think of Synopsys scan tools versus Mentor scan tools? Was one better than the other? Or if you use static timing analysis, Synopsys prime time versus Cadence ETS versus Extreme DA. Anything to do with chip design. And just be involved in that discussion. The reason why I'm saying that is because there's basically a global battle being fought out in the engineering world where it's basically Israel versus India. And the conversation is, should I hire Israeli engineers at a very high price, or should I hire a bunch of Indian engineers at a much cheaper price? The only differentiation you can do is make yourself better and make yourself be known as better, and how you have to do that is on the World Forum, be involved in world technical discussions, and prove that you're better just on a sharper, more practice by practice basis. 20 years ago, you could design a chip. One person could design a chip, or a team of like 2 or 3 could design a chip. Nowadays, it's a team. And 20 years ago, the difference was you could kind of handle it yourself. Now, there's so many different software packages and software tools, they call them tools, that you have to know. That's one of the reasons why there's discussion, very in-depth discussion on Deep Chip about what tools are useful, what isn't, how it works and how it doesn't work. Because it makes or breaks a project. That's huge, and so that's why being the person that says use this tool versus that tool and being able to back that is very important. And it's not a commercial feel-good endorsement thing. It's hey, I'm using this and here's how it works. Here's the gotchas. Here's where it messes up. Here's where it does well. That's real discussion. That's why engineers want to read Deep Chip, and that's why it's to your advantage as an individual contributor to write in, is because you get your name on that. You get credit for that.